Thank you so much for joining me. There is a network you've never seen but use every second. Right now, as you watch this, the data carrying it is very likely traveling through a cable roughly the width of a garden hose, lying on the floor of an ocean, thousands of meters beneath the surface. Approximately 99% of global internet and AI data traffic moves through undersea cables, not satellite, not the cloud, in any abstract sense, physical cables on the seabed, and a growing share of offshore renewable energy. The wind power increasingly centered to the energy transition depends on a nearly identical class of infrastructure to bring electricity back to shore. This is one of the most consequential engineering systems on Earth, and almost nobody outside a small circle of specialists has ever given it a second thought. What actually lies on the ocean floor? There are broadly two categories of subsea cable. Telecommunications cables are relatively slender, 4 to 5 centimeters in diameter, carrying optical fiber wrapped in layers of polyethylene, copper, and often a steel wire sheath for protection. Power cables are considerably larger, 7 to 21 centimeters across, engineered to carry high voltage electricity across sometimes hundreds of kilometers of seabed, armored with steel wire to withstand the marine environment. This network is not static, it is expanding rapidly. Roughly 119 new undersea cables are expected to be built or to be laid in 2026 alone, nearly double the number laid as recently as 2020, driven overwhelmingly by the explosive growth in data demand from artificial intelligence and the parallel build-out of offshore wind capacity. In engineering terms, this is one of the fastest growing categories of critical infrastructure on the planet. Why exposure is rising at the exact moment dependence is peaking. Here is the engineering tension at the heart of this story. As dependence on this network has grown, so has its physical exposure, and those two trends are colliding in real time. Undersea cables have always forced and faced routine physical risk. Fishing trawlers, ship anchors, natural seabed movement, and the ordinary wear of a hostile marine environment. What has changed is a geopolitical layer now overlaid on the top of that baseline risk. Investigators and maritime security analysts have documented a rising number of incidents in specific corridors, particularly the Baltic Sea, and separately waters near Taiwan, in which commercial vessels in several documented cases linked to what investigators describe as shadow fleet. Shipping networks have been found to have dragged anchors directly across cable and pipeline routes. I want to be precise about what it is and is not established here. Attribution in many of these cases remains contested or officially unconfirmed. Some incidents have been characterized by national authorities as accidental, others as deliberate, and investigations in several cases are still ongoing. What is not in dispute is the pattern itself. Since late 2023, at least 11 undersea cables and pipelines have sustained damage in the Baltic Sea alone, a rate of incidents well outside historical norms for a body of water of that size. A pattern of incidents reported factually. A short factual timeline helps illustrate the pattern, independent of any attribution debate. In September 2022, the Nord Stream pipelines sustained significant damage through to 2023 and 2024. A series of separate incidents damaged the data cabling linking Sweden and Estonia, the Baltic Connector gas pipeline between Estonia and Finland, and cable systems connecting Taiwan to the United States, South Korea, and Japan. On December 25th, 2024, the tanker Eagles S damaged the East Link II electricity cable along with three additional data cables connecting Finland and Estonia, and on the final day of 2025, a telecommunications operator detected a significant disruption on a fiber line connecting Helsinki and Tallinn. Each of these is a discrete, documented engineering failure with real economic and connectivity consequences. Taken together, they represent a structural stress test of a global infrastructure system that was, for most of its history, engineered primarily around accidental damage and natural wear, not around a materially elevated rate of deliberate or suspected deliberate interference. How the world is responding, monitoring, patrols, and policy. The institutional response has moved quickly, and it spans exactly the three domains we opened with: security, technology, and energy policy. On the security side, NATO launched Operational Baltic Sentry, deploying frigates, maritime patrol aircraft, and naval drones specifically to monitor and protect underwater infrastructure in the Baltic corridor. On the policy side, the European Commission introduced a €347 million subsea infrastructure initiative in February 2026, alongside a formal cable security toolbox, the largest EU-level investment to date in this space, focused on surveillance, cross-border coordination, and new redundant infrastructure. In the United States, the Strategic Subsea Cables Act of 2026 has moved through a committee focused on interagency coordination, diplomatic engagement with allies, and improved threat information sharing with infrastructure operators. I will note, in the interest of staying within what I can responsibly assess, the specific policy tool here: sanctions, regimes, military posture, legislative frameworks, are properly the domain of policymakers and security specialists, not engineering analysis. What I can speak to with confidence is the engineering response, which is where this story becomes genuinely constructive. The engineering fix: redundancy, sensing, and resilient design. From a systems engineering perspective, the response to this kind of distributed physical risk follows a familiar and well-understood logic. You can't fully eliminate exposure in a system this large and physically disrupted, so you engineer for resilience instead. That means three things in practice. First, redundancy: multiplying the number of independent routes so that any single cable failure, whatever its cause, doesn't sever connectivity entirely. This is a core person behind the accelerating pace of new cable construction. Second, advanced sensing: modern fiber optic cables can now function as distributed acoustic sensors along their entire lengths, detecting the vibration signature of a dragging anchor or unusual seabed activity in near real time, turning the cable itself into an early warning system. Third, faster repair capacity: investment in specialized cable repair vessels and streamlined maintenance logistics so that when damage does occur, restoration happens in days rather than weeks. This is fundamentally the same resilience engineering logic that governs how we design robust power grids, aircraft systems, or any other critical infrastructure where perfect prevention is impossible. Assume failure will occur somewhere in the system and engineer the system so no single failure becomes catastrophic. We tend to think of the infrastructure that runs our world as either fully invisible or fully secure, out of sight, and therefore we assume out of harm's way. The evidence from the last 3 years says otherwise. The seabed cables carrying nearly all of our data, an increasing share of our energy, are exposed, physically and touchable. And the response to that reality, done well, looks less like alarm and more like the same disciplined engineering logic that has made every other critical system in modern life more resilient over time. Thank you so much for your presence. Looking forward to see you in the next lecture.